So welcome back. I'd like to introduce Matej Zaharia, who will be our presenter today. Matej is a graduate student here at Berkeley in the AMP lab and works on cloud computing. And he's going to spend half his time telling you about old cloud computing technology, which is to say MapReduce, which is very widely used, and also half the time on his own system called Spark, which is not only much faster, it's been adopted by companies like Yahoo, Intel, and Adobe.
Okay, thanks Jim for that introduction, and thanks folks, I guess, for coming to the talk. So I'm going to talk about this kind of cloud computing or big data type of parallel processing, and I wanted to cover both MapReduce and Spark, partly because Spark is something we're developing here at Berkeley, and also partly because the kind of API that it provides is starting to pop up in more places as well. So it's really, like, I think if you want to understand where these things are going, it's an interesting thing to look at. It may not be the final answer, but at least it shows you where you can go after MapReduce. So let me start. Just kind of to set the stage, I'm going to spend about half the talk on MapReduce, which is Google's programming model that has now been widely adopted beyond that, and then I'll talk about the limitations that it has and what motivated Spark. After that, I'll explain a bit about Spark, and I'll also talk a bit about our current research. So let me just start with the big data problem in general. So I think everyone's kind of seen a little bit about this. Basically, the problem that all these systems are tackling is that in a lot of fields, data volumes are going faster than the speed at which you can compute on a single machine. And it's really caused by three different trends. So the first trend is that we have data sources that are accelerating. Both in the industry, you have consumer data, for example, in the web or from mobile applications, that is growing quickly because more people are starting to use these. But also in science, you have things like particle accelerators or gene sequencers that are producing a lot of data, often quite a bit faster than Moore's law. The second trend is that it's cheap to actually store the data. So everyone is storing it. And that's because disk capacity has continued to increase with Moore's law over time. And it's just very inexpensive to store it. But on the flip side, CPU speeds are not keeping up with it. And in fact, even with multi-cores, multi-cores have helped, but they're actually not going as fast as, say, disk capacity is growing. So just to set an example of like why this matters, why you need large-scale parallelism for this, here are some sizes of data from different places. So Facebook, for example, collects daily logs of basically user activity on the site, which they use both to improve the product and to do things like detect spammers or place ads. And that's 60 terabytes of data per day. The 1,000 Genomes Project, it's actually something that was started a while back to sequence 1,000 human beings, and now that's 200 terabytes of DNA data. And Google's web index is more than 10 petabytes of data. Now, to put these things in perspective, first let's look at how much it takes to store one of these things. So you can get a terabyte of disk today for $50, and if you're Google, you can probably get it for half or a third of that price. So if you look at that, look at Facebook's data, for example, 60 terabytes and $50 is basically what is it? It's like $3,000, right? $3,000 a day. So that's not a lot. In fact, if you're Facebook, it would be really crazy not to store this data because you might learn things from it that are worth a lot more to your business than that. Even if you look at Google's web index, which is sort of 3 orders of magnitude bigger than that, you're still looking in the millions of dollars in storage, which is pretty much nothing if you're a company the size of Google. So that's why everyone is actually storing these things. The flip side, though, is that reading data from a disk is really slow. So it's kind of like this big, tank you put data into, but the only way you have to put it into it is through a little straw. So disk read speeds have not increased very quickly. And for example, reading a terabyte of disk today takes about 6 hours. That's a speed of 50 megabytes per second is kind of typical for a disk today. Some disks might be like twice as fast. But this is why you need basically large-scale parallelism. If you had to spend this many hours to scan the thing on a small number of machines, you would never actually be able to process the data. So basically, because a single machine can't process or even really store these data sets, the only solution is to distribute it over large clusters, and this is what people have done. So this is, for example, an image of Google's data centers. They released these nice pictures a few months ago, and they come complete with mood lighting and all kinds of stuff. But basically, it's a bunch of machines. Usually, they buy really cheap commodity machines. They put lots of disks in each one, and they try to do things, to learn things from the data. So the question then is, how do we actually program this thing? So traditionally, when you've looked at, I guess, programming clusters of computers, a very common natural model is message passing between the nodes. This is what something like MPI would do. Now, the problem with message passing, though, is that it's really hard to do when you get to large scale, and it's especially so if you want to use these kind of cheap commodity nodes that companies like Google and Amazon are using. So there are three things that make it hard to do. One of them is actually splitting the problem across machines. To do that effectively, you need to know your network topology. It might be different from data center to data center. And you also need to know the placement of the data because this data is residing on disks on specific machines, and you really want to move the computation near those disks. The second problem is actually handling failures. So when you buy these kind of commodity servers and you start putting thousands of them together, failures really become a sort of an hourly occurrence. So just to give you an idea, a typical server today might have a mean time between failure of 3 years, which is 1,000 days. That means if you put 10,000 of those together, you're going to see 10,000 times the rate of events. So you'll be seeing 10 faults per day. And if you put 100,000, you'll be seeing 100 faults per day, and so on. So the software has to handle these things automatically. And then the final thing that's a problem, it's actually even more common than failures, it's called stragglers. It's where a node hasn't just outright failed, but it's simply slow. So there are many reasons this can happen. It can be contention, it can be sort of bugs in the software, or it can be hardware that's failing. If you ever had a laptop, for example, where the disk started to die, you know that at the beginning it's just going kind of slowly, it's making these weird noises, but it still manages to read for a little while. And when you put this many machines together, that's going to be happening on some of them. And of course, if you have a parallel computation, but you're stuck waiting for the slowest node in that, you're not really gaining any benefits of parallelism. So these three things, and especially the failures and stragglers, are, I think, what differentiates this kind of big data clusters from most other parallel platforms, including HPC, because people have really sought to make these things run on cheap hardware and cheap machines. So they become, obviously, they're bigger problems if you have sort of less reliable machines, but this is what people are doing. And it's really to deal with these problems that we need kind of new programming models for this environment. Okay, so what can we do if we're not going to do message passing, and have to make our applications explicitly deal with these things? Basically, the solution has been these data parallel models. So data parallel models, they restrict the programming interface a little bit. You're no longer just sending messages between arbitrary nodes, but they do it in a way that allows the system to do more things for you automatically. So data parallel just means that you give the system an operation that you want to run on a wide array of data, essentially. So there's one operation, I just want you to do it on all these data items at once. And the nice thing about that model is you don't explicitly specify where it runs. So it's not like, I want to send, I'm node 5, I want to send a message to node 7. It's just, get everyone to run this function on this data set. So that means the system has room to schedule where it actually runs it, and hopefully it can do a good job. And the other nice aspect is often you have to give the system basically deterministic operations. And that means the system is actually even free to run the operation twice on different nodes because it's going to produce the same result. So this is how it can recover from failure. It knows what operation you gave it. It just says, I lost some of the output. I just need to do that part again. Okay, so that's kind of data parallel programming in a nutshell. And the biggest example of that is Google's MapReduce. So just a bit of background on this. So MapReduce was basically the first really popular programming model for these large commodity clusters. And Google wrote a paper about it in 2004. And a few years ago, I think maybe 3 or 4 years ago, they said they process 20 petabytes of data per day, like actually going through MapReduce jobs. It's probably a lot more today. And it's really been popularized outside Google by the Hadoop project, which is an open source implementation of it. So Yahoo and Facebook are some of the big users of Hadoop, and I think they each have kind of tens of thousands of nodes now and tens of petabytes of data. Okay, so what is the actual model? So MapReduce is pretty simple. It's just these two operations, map and reduce. And basically, the way it works is your data type is these key value records. So you have files that consist of many of these key value pairs. And then you give it a map function. And the map function is going to do some operation locally on each key value pair. So basically, given an input key and input value, it's going to produce a list of what are called intermediate results, intermediate key value pairs. And then you have the reduce function, and that's going to group together the intermediate values for a given key and produce a list of output values. So basically, map is doing local computation, and reduce is doing parallel aggregation, and is doing it separately for each key. So you can do this on multiple keys at the same time. So just to show what, an example of what that looks like, the sort of hello world of MapReduce is if you wanted to do a word count on a corpus of text. So just for each word, how many, say, lines of text does it occur in? Or just how many times does it occur in the documents? And the way you might do it is you might say, each record here, the value is a line of text. And then in my map function, I'm going to split the line of text into words. And I'm going to output these word, comma, 1 pairs. And then in my reduce function, I'm going to add up the values for each key, which is each word. So I'm going to add up all the ones and get the final count. So this is kind of how you'd program it. And this is what that execution looks like. So essentially, MapReduce is going to divide the input file into these blocks. And it's going to run separate map processes on each block that actually split the text of that into words. The second thing it's going to do, so for the reduce part, the map part was just local, but for the reduce part, we need to bring all the records for the same key together. So it's going to hash the intermediate values. So in this case, for example, the node at the top here is responsible for the. So everyone who has a the as a word sends it to this reduce function up here. The one at the bottom is responsible for other words, that happen to hash to that one. So that's how it's going to work. And then each reduce task adds up the values and gives you a result. Okay, so that's that's a fairly simple way of running things. So when it does this for you, the nice thing about MapReduce is just all the things it does automatically after you've given it the map and reduce functions. So some of the things it does. First, it's going to automatically decide how to split your work into tasks. So this idea of like where do we draw the boundaries between blocks of the file and put map functions, it's going to just do that automatically based on how the data is laid out on the cluster. It's also, when it's scheduling these tasks, is going to send them to the nodes that have that input data. So you don't have to worry, when you run your map about figuring out which machine its data is on. It will handle that for you. And finally, it splits the work into these small tasks, and it's able to load balance them dynamically as machines become free. So if you have, 100 cores in your cluster, you might split the work into 1,000 tasks, and then you load balance it, and then, some nodes might do 9 tasks, some of them might do 12, but overall everyone is doing a kind of equal amounts of work. The second thing it does is it handles different kinds of failures automatically. So there are 3 kinds of problems that it handles. So first, if one of the tasks crashes, MapReduce will automatically retry it on a different node. And in that graph I showed earlier with the map and reduce task, it's set up so that it can replace any one of the tasks with a new copy and sort of splice it into the graph and continue processing. So why is it okay to do this? So for a map, so actually I didn't cover this in a ton of detail. So for a map task, it's okay to rerun it on another node because it just needs to read the input data from the file. For the reduce task, the reason you can launch a new copy is because all the map tasks save the output reliably to disk. So if you launch a reduce task later, you can go back to do it. So this is actually, I meant to show this over here. This is what the little orange disks mean here, is that the map task saves its output reliably. So it's designed so that it can rerun all these things.
Question?
Yeah.
So the assumption is all the data starts on disk and ends on disk here.
Yeah,
right?
exactly, yeah. Yep. So, yeah. And then so this is how you can recover from a task. And then if a task fails repeatedly, oh yeah.
So if the task ends on disk, right, like the map
Yeah.
task, but then that node fails, like do you have to do everything over again? Or what?
Yeah, I'll talk about
Okay.
that, next, yeah. So the other thing here is, of course, if a task keeps failing, maybe it's a bug in the program. So we don't just keep retrying it forever. Sometimes we just stop the whole job. Okay, so that's the fault recovery. That's this one. So one thing I want to mention here is that for this to work, the user tasks have to be deterministic. So they have to produce the same output, and if they have kind of side effects on the outside world, they should be designed to be idempotent so that you can run it again. But that's kind of the assumption in all these frameworks. Okay, the second problem, so someone asked, what happens if a node fails and then you lose the map output files as well? So there are two things that happen then. So first of all, the tasks that were currently running on the node and failed, we have to launch them on separate nodes because they're no longer running. And second, if the node ran any map tasks, now we've lost their outputs, we launch those on separate nodes as well, just because we lost the outputs. Now, one cool thing about this that's a little bit subtle is when a node fails, the work to recover what it did is actually parallelized across the other nodes in the cluster. So if a node did 100 seconds worth of map tasks and then it failed, now you have to run those again, but you still have 100 nodes left. They will each do 1 second worth of work and then they'll recover. So it's not really just going back to square one. It actually, because the work is split into these small units, it can recover quite quickly. And then, yeah.
So I just had a question about the map tasks. So since you're running many map tasks, each one essentially processes a portion of the input file. So I'm assuming that the master actually keeps track of which map tasks.
Oh yeah, definitely.
Okay.
Yeah, I haven't talked about it, but yeah, the way it works as a system is that there is a master that decides how to split the work into tasks and keeps an eye on them and detects failures and so on. Yeah. Okay. So that's the node crashes. And then the final thing is if a node is going slowly, this is the problem I talked about before of stragglers. So this is, again, it's actually an important problem because if you don't deal with it, you just end up going as slowly as the slowest node. And the nice thing here is because the model is deterministic and because it's designed to let you splice in a new copy of a task when something fails, you can deal with stragglers through what's called speculation, which is you just launch a second copy of the task on a different node, and then you see whether that finishes faster than the original one. So if you have one node you suspected of being slow, you can just launch its task somewhere else. And once it finishes, you just take the result of the first one. Okay. So that's kind of how how the model works. And in practice, these things allow you to actually process data on sort of real clusters with real stragglers and failures, and those are just little blips in the execution. Okay, so the kind of final thing I wanted to say about MapReduce is just give you an example of how you'd use it in more complicated applications than word count. So it turns out even though the model is really just these map and reduce operations, you are able to do a lot with it. So just to give you some application, there's been a lot of work actually on fitting different algorithms into this. So one thing that's really natural to do in it is just search. So search is you just have a large data set, you want to scan it and pull out the records that match, say, a given pattern. And the way you do that is in the map function, you would just basically have an if statement. So in the map function, you can output any number of intermediate records you want. You'd only output one if the line matches the pattern. And then in your reduce function, you don't actually need a reduce function here. You can just use the identity and just get all the values that came out of that. So that's one of the use cases that Google could do with this. Sorting is another operation that's pretty easy to fit into the model. So basically in sorting, you have these key value records as your input, and you want to return the same record sorted by key. And actually, this you don't even really need to write any code for this. The way you do it is the map and reduce, you just use the identity function, but then there's a way to control the partitioning of keys across the reduce task, so you can use that to actually sort the data. So when you run your reduce, you're able to set this partitioning function. So for example, you say this reduce task gets keys A through M, this one gets keys N through Z, and now you've sorted the data into these two buckets. And even locally, actually, MapReduce can do a sort on the data before it passes it through your identity function. So you just pick a partitioning function that preserves order. And another interesting thing is inverted index. So this is kind of the really toy version of building the Google Web Index. So the data here is you have a bunch of files, which maybe the key is a file name, and the value is the text of that, like the contents of a web page. And you want to output the list of files containing each word. So the way you do it is in the map function, you basically reverse kind of each pair. So you get, as your input, you get a text, you split it into words, and you output this word and then the file name for it. Then in the reduce function, you've got for each word the list of file names that contained it, and you just make that list unique. So you just remove duplicates, and now you have your inverted index. So here's what that looks like, just to give you a sense. Basically, we have these two files here, and they each contain text. For each one, we output each word and then the actual file name of that. And then when we group together these values by key, we get, for each word, for example, B happened in both documents, so you get a list of both of them. Afraid happened only in this 12th night, so you only get that one. Okay? So that's how that works. And then a final thing you often do is actually, for more complicated things, you build them out of multiple MapReduce steps. So say that instead of doing the inverted index, we wanted the most popular words in the corpus. Now for this, you can't really do it in one step because you need to both count the results and then sort them. So it's a combination of like the word count and and sorting. But you can do it using two stages. So for your first stage, you could build the inverted index we had before, which is basically for each word a list of files that contain it. And then for your second stage, now you have basically the sort job again. You want to sort the words based on a number of files that contain them. So you could map each word, and the list of file to just the count, like the length of the list, and then the word, and then you could sort these things. Okay. So that's that's one way to run this operation. Okay. All right. So basically, just to summarize this part, when MapReduce, really it provides this data parallel model, and the interesting thing about it is that given that model, it can do a lot of things for you automatically to deal with these clusters. So it can automatically split the job into tasks, do locality-aware scheduling, handle load balancing, and also handle fault recovery. But the story doesn't actually end here. So this is just one of the first models, and there are actually lots of things you can do better than this. So next thing I'm going to talk about is sort of the limitations. Before I go there, are there any questions about this so far? Does it make sense? Okay. Yeah, I've sped a little bit through it because I think some people may have seen this before too. Okay, so what are actually the limitations of this? So essentially, the MapReduce abstraction itself was really useful, but the place where it falls short is that often when you write a parallel algorithm, you need to write it as a series of many MapReduce steps. So it's a really natural thing, when you have an abstraction like this, you want to compose it, use it multiple times in an application. So just to give some examples of that, I showed the top K count before, but lots of real applications have many MapReduce steps as well. So Google's indexing pipeline, for example, was 21 steps of MapReduce when they published their paper. A lot of data analytics queries, which is what people do with these, is basically computing reports about, say, how users are searching for different terms on Google. They also need to do these multiple phases of grouping and counting and sorting. So for example, if you want to group, you get, say, records that are users clicking different links, and you want to group them into sessions, you need to bring together all the clicks for a given user ID to the same machine. That's one MapReduce. And then maybe on top of that, you want to do a top K or a sort or something like that. So real queries often have, sort of the low numbers, 2 to 5 steps. And the other case where this happens is if you have iterative algorithms. So a lot of the more numerical algorithms you do on large data are iterative. They're basically optimizing something in multiple steps. An example in the web is PageRank, but a lot of, say, machine learning and optimization algorithms are iterative as well. So having these multi-step applications creates two problems, really, programmability and performance. Okay. So what is the programmability problem? So the problem is that if you just use the MapReduce model, you end up with a lot of spaghetti code. So for each job in, say, your 21-step Google web pipeline, you have to write a map function and then a reduce function, and then you have to write something at the bottom that glues them all together into a pipeline. And it just ends up being spread out into a lot of files and functions that are not really running in a clear order. For each step, you actually need to create a lot of boilerplate code. The code I showed earlier was a little simplified, but I'll show you what the actual wrapper code looks like in a little bit. And finally, when you combine these things together, you don't even have type safety. So if you have a step that outputs, say, strings, and then you have the next map function expects integers, and you run it on that same file, you're just going to get some weird runtime error because you combine these.
So to use the language from an earlier lecture, the pipe and filter pattern is not enough. Yeah, okay, yeah. Mm-hmm. Yeah. Okay, so that's kind of, yeah, these are the programmability problems. The other problem you have, though, is also performance. So MapReduce really only handles this one pass of computation, one stage of map tasks and then reduce tasks. And actually, as Jim was pointing out earlier, in between these, you always write data to the file system. So you write it to this replicated file system, which is on disk. You need to actually send it across the network to multiple nodes. And that's actually quite expensive. So if you have applications that need to reuse data, actually, when you profile MapReduce, it's spending a lot of its time just writing data to the file system and then reading it back. And there are really two cases when you need this. So one is the multi-step pipelines or algorithms, like I talked about before, say the web indexing or the PageRank. But the other case where data reuse happens is actually interactive data mining or exploration. And that's what a lot of users of these clusters actually do. It's not just running, say, web index every night, but it's a person sitting in front of the screen and trying to figure out, say, why Facebook users, in France are not using photos or something like that. So they're trying to compute different statistics about the data. And to deal with this problem, really, it's hard to just deal with it in the MapReduce model. One of the things people have done is actually hand optimize the algorithm. So even if you want to write the algorithm as a bunch of separate map and reduce functions, you're going to merge them together, merge some of these steps to make it run faster. But then the problem with that is actually, it makes the code even messier than kind of what I mentioned before. Okay.
So the Spark project that we had really aims to address both these problems, and basically it does this, through two different things. So first, for programmability, in Spark, we created this very concise functional API. So based on functional programming, where you can chain together a bunch of functions in kind of the same line of code if you want, and you don't have to create these separate map and reduce functions for each one. And so what this means is, so basically the model is you get a whole bunch of different parallel transformations you can do on collections, and you can chain them together very quickly. What this means in practice is you often get 5 to 10 times less code than MapReduce. The other thing we did in Spark is that's actually really useful just for exploring data is we made it possible to use it interactively as well. So we do that from the Scala and Python shells. Python, I think everyone's maybe seen. Scala is sort of this functional language that runs on the JVM. So it's like Java with functional programming. And I'll show a little bit of what that looks like later. So that's kind of the programmability. On the performance side, there are two things we do. One of them is we add support for in-memory storage between steps of your computation. So you don't have to go back to the file system and go through the overhead of that. And the second thing we do is we automatically optimize operators. So this problem I talked about before where you want to write your function, your code as a bunch of, say, different map functions, but for performance you had to squish them together into a single one, the system will do this for you automatically. And I should say also, Spark is one system that does this. It's not the only one. So I can definitely talk, about other systems that have done this. And even people using MapReduce on the back end today actually are designing APIs that look a lot more like this today, including Google. Okay. So just to give you a sense of sort of the programmability benefits, so this is, if you really want to write word count in MapReduce, this is kind of the example from Google's paper, and hopefully you can kind of see the code. I mean, you don't really need to see it, but basically the problem is, you have your, say this is your map function. Even though your function is just a little bit of code there that splits each line into words, you need to create all this wrapper stuff around it to put it into a class. And then you need to register it with the system. Same thing with the reduce function. Really, you just want to add up a bunch of counts, but you need to create this wrapper code. And then you have this kind of main function here that sets up the job as a chain of these operations. And you have even more kind of boilerplate code over there to do it. So this is what I was talking about with that. If you want to do this word count in Spark, the code you end up with is just this. So it's basically, it's really condensing and removing a lot of that boilerplate. And this is Scala code. If you're not familiar with Scala, I'll explain a little bit. But basically, you can see it's quite a bit shorter. So essentially what you do is you say, okay, I have a text file in my HDFS is the Hadoop distributed file system. And then I want to run, I have two types of map operations here and then a reduce. And then I want to save the output. And this is kind of the whole program. You could put it inside a main and have it actually run. The way you use Spark is you pass these functions, basically these function expressions to your operations. So flat map takes a value and it takes one input record and produces a list of outputs from it, maybe more than one. So here's just going to split each line into words. Then map takes one input and creates one output record. And then reduce takes two values and adds them. And this is kind of the syntax for doing that. Okay. The second thing, so apart from the programmability, the model also helps with performance. So if you have these iterative algorithms that do many steps, you can go a lot faster using Spark. And that's primarily because we can keep intermediate data in memory in an efficient way. It's also partly because we can pipeline together more steps. Okay. So in the rest of the talk, I'm going to go through the concepts in Spark in a little bit more detail and also show you, so like unlike the examples before, which are mostly text processing, I want to show you how to do some more numerical things with it as well. Yeah, any questions on this? Okay, great. Oh, yeah.
In the example code from Scala, how much code are we not seeing?
Yeah, the only thing you're not seeing is there would be one line to initialize Spark, and then there would be your kind of like basically like a class around this to turn it into a program. So there would be, like class word count, and then function main, and then you'd have one line to initialize Spark, and then you'd have some curly braces around it. Yeah. So it's, yeah, that's a fair question, but it's like 3 extra lines of code. Yeah. Okay. So I'll show you some actual programs with this as well later. Okay. So basically, how do you use Spark? So there are kind of 3 concepts in it. So the first one is your distributed collections of objects. So these are something we call resilient distributed data sets, or RDDs. The resilient is because they are fault tolerant. So we can automatically rebuild these collections if data goes missing. And the way you work with these, they're a lot like the files in MapReduce, actually. So they're immutable partitioned collections of objects, and you can, unlike MapReduce, you can choose to cache them in memory if you want to quickly reuse them. Next, you have operations on these data sets. And there are 2 types of operations. Transformations, which build a new RDD from previous ones. So these were things like the flat map and reduce that I showed before. And actions, which are things that compute result. So the way it works is transformations build up kind of a plan of execution, but nothing happens until you run an action. And when you run that, the system automatically decides how to schedule and optimize it. And so actions are like the save I showed before at the end, which said, after you've defined this data set through maps and reduces, save it to an output file. And the final thing you get in Spark, which is actually kind of interesting to comparing with other programming models you guys have seen, is these restricted forms of shared variables. So if you looked at OpenMP, I don't know if you guys looked at OpenMP, but I think one of the lectures covered it. You have these special shared variables with semantics like I'm going to add to this value over time, and we added the same thing in Spark. Okay. So just to give you an example of how these things work together, I'll do a slightly more detailed one than what I had before. So this is, you have maybe some log file on the cluster, and there are some errors happening on a website, and you want to load the error messages into memory and search for different patterns. So this is going to be our cluster. I'll show how things actually execute, and this is, on the left is going to be the code we type in. So first thing we're going to type in is create a data set which represents a text file in the file system. And this is our base RDD, so it's a collection of lines of text or strings. Next thing we can do is some transformations. So filter is a transformation. It just keeps elements that pass a function. And then the code in there, the underscore that starts with error, is Scala's syntax for a function literal or a closure. So this is like basically like lambda x that starts with error in Python. So the thing about this is you can basically you can call into any code you want in here, and if you don't want to write the function in line, you can also put in the name of a function you have in your program, and will automatically take that function and run it for you on the cluster. So this is just calling the Java starts with. And so this gives us a transformed data set called errors. We can do more operations on this. So we filtered out the error messages. Maybe the lines of text are tab-separated fields, and we want to pull out field number 2. So this is how you do that in Scala. Basically, you split each line by tabs, and then this is kind of like array indexing. So it's pulling out element 2 of the array. And finally, you can tell the system which data to actually cache in memory. So here, maybe the whole file doesn't fit, but the messages do, and we want to keep them around because we'll ask a bunch of queries. Okay, so at this point, nothing's actually run on the cluster. So the system just remembers these operations and will come up with a plan when you actually need a result out from it. So that's what we'll do next. So next we're going to see how many of these lines, for example, contain foo. And we're going to do another filter and then a count. So count is what's called an action. So count has to return a number back to your program, so it can't be lazy. It has to actually run things. And so at this point, the system is going to look at the whole plan so far and decide and divide it into tasks. So first thing it's going to look is where does the data lie on the cluster. So maybe your input file is split into blocks and they're on different machines. Next is going to send tasks to those machines to do the processing. Now, in this example, we had both a filter and a map. It's actually going to do those together as part of the same task. It's going to fuse them into one kind of map task because it knows that the output of the filter just goes immediately into the map. So you don't need to save any data in between them. So each machine is going to automatically, is going to process its blocks, send the results back. And then the final thing the system will do is build up a cache of any cached data sets you created along the way. So now you have partitions of these messages sitting in memory. Next time you do a query on it, for example, maybe foo wasn't the problem, you search for bar, it's going to actually reuse the data in the cache. So the job scheduler is now going to know, okay, the result up to this map is in these cache blocks here, and so it's going to just read those, and return some results. Once you've done this, you can do quite a bit more than just filters. So we have a whole bunch of operators, including reduce and group bys, joins, sorting, and so on, that you can just call in. So to give you a sense of the difference this makes, one of the tests we did is kind of full text search of Wikipedia. So like just say you're looking for statistics about different words in Wikipedia. If you do this with an on-disk MapReduce system like the open source Hadoop one, it takes about 20 seconds to scan through all of Wikipedia on 20 Amazon machines. If you do it with an in-memory data set, it takes about half a second. So it really kind of gives you this significant speed up if you have applications that reuse a lot of data. And we have also been able to do this with quite a bit larger data sets. So even a 1 terabyte data set on 100 machines, we're able to do a full text search in about 5 seconds. Yeah.
So just curious, you've got this is a little bit coarse-grained, I guess. You've got many different options for how fast of memory to buy and put in your machine. You can use SSDs or hard disks.
Yes.
Is there sort of a trade-off spectrum in there? If you use SSDs, you get 10 seconds, or how does that break down with different
So
hardware?
SSDs are a little bit faster in terms of throughput than disks today, but actually not a ton. I think maybe a factor of 4 or 5. They might get faster with a better interconnect between the SSD and the processor. But yeah, in practice, you may want to have a hierarchy of memory, and the system actually supports different levels of storage for each thing, but we haven't played too much with SSDs. So I think that's an interesting question to look at. Yeah. Yeah, I can.
If there's some data that's cached on one of the nodes and that node goes down, will it has to regenerate?
Yeah, exactly. So this is actually, so in Spark, we kind of generalized the recovery mechanisms in MapReduce. So even for a long chain of operations, you can rebuild the missing data. And that's what the resilient comes from in the name, is that the data is automatically rebuilt. Yeah. So I'll talk about that next. So basically, to do fault recovery, the data sets that you build in Spark also automatically track their lineage, which is basically the sequence of operations that we used to build them. And this is what we use to actually recover it. So in the example before, for example, we had a filter and then a map. We're going to create a lineage graph that looks like this. So we'll remember we started with a file, we did a filter with this function, and then we did a map with this function. And so the scheduler inside the system knows this graph, and when it's missing data, it can rebuild the missing slices. Okay, so I thought this showing you things on the slides is is one thing, but I thought since this is really all about making this stuff a lot faster, I would also show you a demo just so you can see what you can do with the system. So let's see whether the demo is still up. Yeah, it seems to be up. My internet is also still up. So basically, this is going to be the Wikipedia search demo I mentioned. And what we have here is we have a cluster. I launched this Amazon EC2 cluster with 20 machines. And they each have 4 cores and like 4 disks. So they're not like super small machines. And I loaded Wikipedia onto it, which is about 60 gigabytes of data. 60 gigabytes is not at all huge compared to the data sizes I was mentioning before. But as you'll see, even this, like actually reading it in parallel from 80 disks, takes a substantial amount of time. So this is kind of the Spark interactive shell. For all the operations I showed, you can run them not just in a standalone program, but also in the Scala shell. And this is kind of like your Python interpreter, for example. You just type in code, and the system, and you know, it gets evaluated. But because it's the Spark shell, it has a special variable Spark context, which is used to run operations on the cluster as well. So the way you actually use this, and you can actually do this demo yourself on EC2 if you want, is you first you know, load in a file from the file system. So here I put this file on the distributed file system that's on this cluster, wiki.tsv. It's a tab-separated values file for Wikipedia. And this is just a collection of strings. So you can see these RDDs have a type which is string, and the language is actually type safe. So you can't treat that string as an integer or as a double or something like that. Now, if one of the things you can do, you know, before we do anything in parallel, is you can also explore the data locally. So I'm going to do file.first, which is just give me the first line of text in the file, and the file looks to you much like a collection would in say a Python or Java type language. So it's a collection of records, and you can peek at the first record. So this is the first line of text in the file, and this is basically a tab-separated values format. So each line of text is one article, and it has 5 fields. It has an article ID, it has a title, it has a date modified, and it has an XML version of the article. And then you don't see the last field, but it also has a plain text version at the end. So some of the things you can do now, so even in the Spark shell, you can actually define other types of data structures to represent the data in a nicer way. So in this case, I'm going to define a class to represent each article, and I'm going to pull out only 2 of the fields, the title and the plain text. Okay, and I just defined a class in here. And then I can actually do a bunch of map functions and turn my collection of strings into a collection of article objects. So this is going to be a bunch of this underscore stuff, which is the way you can specify functions in line in Scala. So first we're going to split each one by tabs. And then we're going to filter. So some of these lines of text don't have the plain text field, the last field, because they're things like images. So we're going to just filter the arrays whose size equals 5. And then we're going to map. And now we have this array of fields. And we're going to create a new article. And we'll take A1, which is the second field, the title, and A4, which is the 5th field, the plain text. So now I have this collection of articles, and you can see this, this didn't actually run anything on the cluster. It just kind of lazily defines these transformations. But if I want, I can also peek at this one. So for example, title of the first article is this and yet, it's still that initial thing. And the text of it is whatever and yet is, which is some kind of musical thing. Okay. And then final thing, final thing I'm going to do is tell the system to cache these guys in memory, so that when we run something on the cluster, it will remember them. Okay, so now let me do something in parallel as well. I'm going to just count how many of these articles contain Berkeley. And let's just do that. And so now it's going to actually run this in parallel. So it's taken the function I passed in there, and it's actually running it on the cluster. And it's taking a bit of time to do it, but basically it split it into these 480 tasks, and it's going ahead and doing them. And it did it, so the answer is 15,000 articles contain Berkeley, but it took about 20 seconds. So that's not exactly interactive. Now, though, since we've done this and we called cache before, the data will be sitting in memory, just the article objects, not the original text. So we can actually do this again, and we can get the same answer, quite a bit faster. And in fact, because we loaded the objects, so not just remembering the result of this query, but we just have that data, we can ask other queries as well. So for example, the one I like to ask is actually Stanford. So these guys had 15,000. Stanford only has 30. So that's one of the things. So there's a few other things I want to show that are kind of cool. So one thing is you can actually define variables in your shell and then use them in these things. So we defined a variable there, now we're going to use it in our function. So when we pass the function, we actually pass any variables you're using in your scope as well. And MIT also has fewer hits than us, so that's kind of a nice thing. It makes it easy to actually explore with this data the way you would with local data. And then the final thing I want to show is also the sort of fault tolerance. So I talked about how we remember the graph and we recompute things. Yeah.
Since this is a shared resource, how do you know you won't get swapped out?
Oh yeah, how do you know you don't get swapped out? So now we have very simple, so you mean EC2 is a shared resource, or?
When you bring it into memory, so to speak,
yes.
Aren't you sharing the cores and its memory with other processes?
Yeah, you are. So we don't know. We could be swapped out by Linux. In practice, on these machines, we just don't have swaps. So, and yeah. Actually, I think a lot of people who run the data center machines don't set up swaps because it's too unpredictable. So I think that's actually somewhat common these days. But
so you own the resource for the length of the job.
Yeah, we do own it. But in your application, you might still create more data than fits into memory. So we actually do our own swapping. Essentially, we spill data out to disk, and we can support like half the data being in memory, half being on disk. Yeah. Yeah. So the final thing I want to show is also the fault recovery stuff. So as I said in MapReduce as well, so these things that do recovery through recomputation, they can be quite fast because recovery is done in parallel. So what I'll show here, so I had here 20 nodes in the cluster, and actually, let me just refresh this. Yeah, so there are 20 nodes, and I'm just going to take one of them at random and sort of kill it. This is kind of the EC2 machine going away. So it takes a little bit of time for it to shut down, but if you refresh, eventually it's now at 19. So one of them is actually gone. And if you look here also, it says, okay, we've lost the data on this node. So the cool thing that happens there, say we just run this guy again, you can see, most of the tasks finished quite quickly. They were on the data that was still available. And then we were left with about 20, 30 tasks that had been on the failed node. But those we finished in just about 4 seconds. So that's because we automatically split that work among the rest of the cluster. So this is kind of what I was mentioning before with MapReduce as well, is that even when a node fails, the impact on the job can be very small because these data parallel models allow you to parallelize the recovery as well. So that's how that works. Okay. So hopefully it's given you a bit of an idea of what you can do, and also why it's exciting to be able to type this code very concisely and also do it interactively, because it can really change the way you can actually work with data. So in the rest of the talk, I'm going to cover a few other things we added, we have in Spark, and also a few other examples. And then I can also answer questions. We'll see how that works out. So apart from doing these kind of text search workloads, Spark is also good if you have anything with any kind of iterative algorithm. And one place this is really common is machine learning algorithms, which are basically a lot of mathematical optimization. So a lot of these are essentially gradient descent. So one example of this is logistic regression. This is a thing you'd use for classifying points. So for example, say you have spam and non-spam emails. The way you'd build a classifier is you represent them as features in some high-dimensional space, like say number of occurrences of each word in English, and then you label the spam and non-spam, and you want to find a hyperplane that separates these guys. So the way a lot of these algorithms work is basically gradient descent. You start with a random value, and then you compute a gradient, which is, you have a function with how well the line is separating the points. You compute the derivative of that. And that's done as a sum over all the points. And the gradient essentially gives you a direction to move the line in to improve the separation. And you keep repeating this process, this parallel sum, and then moving the line, and eventually you converge to a good separating plane. So the thing I want to point out about this is, it's a lot of parallel MapReduce style operations, these sums, on the same data. So if we can keep the data in memory, for example, it's going to be quite a bit faster. So this is the code if you want to write that in Spark. And again, this is kind of real code, and it shows why having the functional model can make it very concise. So basically what you do here is you'd say, take a text file, maybe that your data is text, you map it into these point objects, and then you cache them in memory. And then you'd start with a random vector, which is your separating line, and you do these iterations. There's just a for loop in your program where you're doing maps and reduces. And you don't need to know exactly what it's doing, but eventually this is going to converge to the right value. Okay? And so this, much like the demo I showed, so you can use variables in your main program in here, and they'll be shipped to the cluster. And this is kind of the performance graph. So this is a thing where obviously keeping the data in memory is very helpful. And basically the interesting thing here is the amount of computation you're doing per byte of data is really small. Actually, it's basically just the dot product you're doing on each vector. And so being able to read it at memory speed instead of disk speed actually makes your whole application many times faster. Okay. So this, yeah, okay, whatever. This, I don't need to go into that. So the other thing I want to mention, apart from these simpler kind of map and reduce operations we showed so far, we also implemented a whole bunch of other ones in Spark. So if you use it, this will save you a decent amount of time over having to implement these things from scratch in MapReduce. All of these you could also implement in MapReduce based on map and reduce itself, but because we provided them for you, you have an existing implementation to use. And I also want to mention that even though the examples I showed were mostly in Scala, we have APIs in Java and Python. So the Java one, you don't have functional programming really, so it's a little bit messier. You have to define a kind of a function class inline, but you can still do it. And the Python one's actually really clean because Python has these lambda expressions you can pass in. Okay. So the final thing I want to mention about the programming model is these shared variables. So how are we, this is another way that we're extending it beyond just this idea of data parallel operations, map and reduce, but we're somehow sticking with the model that we had before, which is, your parallel computation looks a lot like a local program. Basically, in what you've seen so far, you've seen a bunch of RDD operations, and you've seen that they can use variables from outside their scope in the program. And the way that happens is that when we send a task to a machine, it gets a read-only copy of that variable. So there's no sharing. It's just, if you have like the query that we had before, the MIT, you don't get to modify that inside your tasks. But this is also a nice place to enable other sharing patterns. And there are quite a few patterns that we can enable and still retain the fault tolerance of Spark. So just as an example, one other thing, this is one of the applications we tried to do early on, which is collaborative filtering. So this is another machine learning algorithm, and basically the goal here is you have say user ratings for products such as a movie, and not every user has seen every movie, but you want to predict how much they'll like a new movie based on the ones they've liked so far. So this is, for example, what the Netflix challenge was. And basically, the way you do it, you'd model it as, okay, there's this hidden matrix R of how much each user hates each movie, and we don't know all the values in it, but we've seen, for example, user 1 liked this movie here, and then user 2 also liked the movie. So that means that user 1 might like this one, and user 2 might like this one, because hopefully the users are somewhat similar. Or you might look at movies themselves. You might say, people who like this particular movie also like another one. So how do you actually do this kind of prediction? There are many methods, but one really common method is called matrix factorization. And basically the idea there is we'll model R as being the product of user and movie matrices that are smaller, lower rank. So essentially, the way you model it is you say there are kind of K features, and each user has a value for the K features, and each movie has a value for them, which is its column in this matrix. And then when you multiply them out, the rating is like the dot product of those vectors. So what are the features? So for example, you might say, is a movie romantic, or is it, futuristic, or whatever, is it funny? These might be the features in your vector of K. And then for each movie, you'd have a score, I guess, in its column vector. And for each user, you'd have kind of a weight, like do they like that in a movie or do they dislike it? And then when you multiply these matrices, essentially in each cell, you have, the dot product of those two things. So once you have this model, one way to optimize it is, slightly a more complicated iterative optimization algorithm than before. It's called alternating least squares. And the way you do it is you optimize A and B, you take turns optimizing each of them. So you start with random values for them. You multiply them, you'll get something that doesn't really look like R. And then then you keep the user vectors A fixed, and you optimize, you keep the movies fixed, and you optimize the user vectors based on that to minimize the difference from R. And then once you've gotten a version of this matrix A that's pretty good, now you keep A fixed, and you optimize the other matrix B to lower the difference from R. So it turns out if you actually do this, you'll converge to a local minimum here, and you do it a bunch of times, you actually get a pretty good factorization overall. So this is how you would write that. First, if you just wanted to write it serially in a Scala program, so one way to write it would be like this. You'd say, okay, R is we're going to read a matrix of ratings. A is some random vectors, one for each user, and B is some random vectors, one for each movie. And then we're going to have these iterations, and essentially on each iteration, we first update A. So for each user, we update it. We kind of solve this least squares problem to find the best vector for it, given B and R, which are the known ratings and the movies, the movie's current features. And then we update B by holding A fixed and doing again a least squares thing. So one nice thing about it is that you can update the users and the movies in parallel because you're just doing a separate kind of least squares calculation.
Are these plain old least squares, or are they non-negative constraints?
Ooh, I think they're actually plain least squares because I think you can have I think you can have like a negative weight for a feature. Like you really don't like futuristic movies. Yeah. Mm-hmm. So this is kind of how we do it. This is in Scala. If you write it this way, this is like the range 0 until m. if you do it in Spark, so the naive way to do it is to just parallelize those maps we were doing before. So at the beginning, we're going to have to do a bunch of these least square calculations for U users. Let's just do that in parallel. So one way you can do it in Spark, you can take any local collection and make it parallel using this parallelize function. And that's just going to split it across the cluster. So each machine gets a different slice of it. And then you do a map, and then collect is actually taking a distributed data set, the result of the map, and bringing it back to an array. You could do the same thing for B. But a problem with this, if you just do it naively, is that you have this big matrix R, which is the ratings, and we're resending it to all the nodes in each iteration. And in practice, for the Netflix challenge, for example, I think R was actually like a few gigabytes of data. So it's not really smart to be broadcasting this to all the nodes every time. So to deal with this problem, one of the types of shared variables we added in Spark is called broadcast variable. And basically this lets you mark a value that you're going to share across different parallel operations, and it ensures that each machine only gets that value once. So the code for it is not a ton of extra code. You say spark.broadcast this value, and you get the special wrapper thing around it, so you don't pass in the original matrix to the functions anymore. But then you use r.value to access its value on the workers. And the Spark engine will ensure that it's only sent once to each worker, and then the worker keeps it around. So when you do this, just in this application, for example, we got a factor of 3 performance improvement, and it also improves the scalability, like the number of machines you can scale this out to before it actually, stops benefiting from parallelism. Okay. So that's one of the things we added. And the cool thing about this is, as you saw before, it's important to make these things be recoverable at any time. But broadcast variables, if you have a new machine that comes up and that, say, doesn't have a copy, you can always fetch it from a different machine. So it doesn't mess up the fault tolerance. The second thing we added is, again, similar to things you might see in OpenMP, is an easier way to do aggregation, which is called accumulators. So you can always do aggregation using just the reduce operator, as I showed before for the sums, but these give you a way that looks more like shared variables, which can be convenient if you just want to count a bunch of different values throughout your code. So accumulators are used in a similar way, where basically you tell Spark to make an accumulator with a given initial value, and then in your parallel tasks, you can only use the plus equals operator on it. So actually doing anything else on it is an error, including looking at its value, because you don't know what other machines are doing. But it still looks a lot like kind of your usual code. And then after you run your operations, in the master, you can query its value and see what it does. The nice thing about this, it's very simple, but one nice thing is you can add these at any point in your code, and you don't have to add, say, a new reduce operation and change the way your code looks overall to collect statistics. Okay, and this essentially, the main kind of key of it is that the only thing you can do with them inside tasks is add to them. So because we know when a task succeeds and fails, we can make sure that each task's effect is only reflected once on the output. And one of the interesting things is you can't actually read the value inside the tasks. That's because then if you could do that, even if the master told you its current value, the task would become non-deterministic. And so that would be a problem.
Presumably you could do any commutative and associative operator?
Yeah, you can actually, yeah. So you can actually define your own type of accumulator with your own operation. Yeah. And so this is another case where it gives you, it looks a little bit more like a shared memory model, but it actually retains the efficiency and the fault tolerance of actually running this on a cluster. Okay. So just a couple of other things. So one of the things I mentioned a bit before is the job scheduler. So when all of these operations, when you're using them, we actually do a bunch of work to actually schedule them into an efficient plan. And there's a lot that can be said about this. And you can find there are actually papers on this kind of things, and it's a very common thing in, say, parallel databases as well. But essentially, there are a bunch of tricks you can do. Two of the things we do are pipelining things into stages. So, for example, down here, so these are our data sets, and you're doing different operations on them. Sorry, I keep forgetting to use the mouse for the people on video. You're doing different operations like map and union. We will actually group those into a single task. So because the output of this map goes directly into the union, there's no point saving the data in between them. We can just pipeline them into a single task. We are cache aware, so if you see, for example, that here this data is cached, there's no point doing the group by again. We can just use the result. And the other thing we're aware of is partitioning. So because, for example, here, because we did a group by, the data is already hash partitioned into like 3 buckets. When we do this join operation, which is actually bringing together elements with the same key from 2 different data sets, this data is already hash partitioned, so we don't need to rehash it. We can actually just use the partitions we had before. So the scheduler, given your program, it can do these optimizations for you, and these are the things you'd have to do manually in MapReduce. And then final thing, I wanted to mention about it is this is an open source project, and actually we've been really lucky to have a growing community. So if you're interested, in how people use this kind of thing, like what are the problems they face, say memory management on clusters or things like that, we actually have people that, you can ask about that. So we had training camp at Berkeley. I think we'll do it again in August, where we had 3,000 online attendees, but we also have an in-person meetup with actually quite a few members, and we have 15 companies that are contributing code to the project now. So it's been really like, it's not, I think there's a lot of luck involved in getting this to happen, but it's actually now a resource that we have in terms of like how do real users want to use this. So I think that's kind of all I wanted to cover. I could answer questions now, or I could spend a little bit on future directions, but maybe it's better to just answer some questions. Yeah.
I had one question. Is there any demand for reproducible results when people do, let's say, a floating point reduction?
Oh, yeah. That's a good question. Yeah, so I think, so we haven't really run into this so far, but I think eventually people might want this. It's because of the order you add things in, it may not be deterministic. Something we do want to do actually, we want to check how expensive it would be to always do the reduction in the same order.
We actually have some new algorithms which give you reproducible results, and it doesn't matter what the reduction tree looks like.
Oh, very cool. Okay.
So we can talk about that.
Yeah, that would actually be really cool. Yeah.
Along the same lines, just another question about sort of what users are doing with it.
Yeah.
Are there many people using Spark for like multimedia, stuff other than text, video, images, audio search?
Wait, what do you mean? You mean multimedia other than text?
Yeah. So say I've got a query and I want to look at all the images in my 200 gigabyte database for all the cars in it or something. Yeah,
it's actually some. I don't know someone doing exactly multimedia. There are people using it for numerical data that's not just text. So for example, people doing machine learning things, and they have these data sets that are like, taxi cabs moving around San Francisco or something like that. I don't know anyone doing images, but there are some folks from Adobe that I wouldn't be surprised if they're doing images, because that's kind of what they do. Yeah.
So just sort of a comparison with MapReduce and Spark. So MapReduce sort of gives you a disadvantage in terms of having to go to file system all the time and limiting the communication to just sort of these maps and reduces between all the nodes. So it seems like Spark takes care of the in-memory.
The data sharing. Yeah.
So I'm just wondering, if it also supports a general communication model as well. So for example, some of the newer algorithms in linear algebra, they sort of avoid communication by doing, sort of a little bit more complicated and being a little bit more complicated in terms of the data sharing. So I'm wondering if...
So you mean if it's not just all-to-all, or?
Right, so basically it's, it's sort of replication of the input data.
Oh, I see, yeah. Right. So actually we, there's not, so technically you can replicate the data. Actually, it's okay if the same data resides on two nodes, and sometimes it happens because of like the straggler recovery, for example. We haven't done anything very special with that, so I'd be curious to look at that, because that's one of the nice things about the model is like it doesn't really care whether you have 0 copies of the data or 2 or 5. So if that's useful for you, I think that's actually interesting. Okay. The closest we've done is you have, one is kind of this broadcast pattern, actually. So the broadcast pattern is you want everyone to get a copy of a certain data set because it would be really expensive to have them access it over the network. So you just send it to everyone. Yeah. But I'd be curious. We've been doing, like, another thing we do is, for example, if you do Cartesian product, some people want to do that, you could end up with copies of the data on many machines, and it might be useful. Yeah. Okay.
So if you try to cache something to memory and you don't have enough
yeah.
Does it warn you, or?
Yeah, so actually it does warn you, but one of the nice things about it is that it also degrades gracefully in that case. So that's a good question. So when we designed Spark, we actually wanted it to work with any amount of memory, and part of the reason was that even because of failures, you might lose some of the memory in your computation. So you might have started out with enough, but then you lost lost some of it, and the data doesn't fit in anymore. So we designed it so that actually when data spills out to disk, the operations are all sequential. So it still uses disks at kind of the full speed you could use a disk at. Now that's a lot slower than sequential operations on memory, but at least it's it gives you some graceful degradation. Yeah. Yeah. Any other questions?
Is there a way to so at the very beginning, let's say I set up my first kind of Spark query, and I do a few steps, and then I ask for the result.
Yeah.
Sort of near the beginning, is there a way to say, I'm going to do a bunch more queries like this, especially on this subset of the data. Can you please make sure this subset of data stays in cache instead of just in memory? Can you kind of say where in the memory hierarchy things are going to
go? Okay. So you can't, right now you can't control like the processor's cache. That, I think, that would require some help maybe from the processor or operating system. So we didn't do that. The closest thing you can do is we are talking about lower levels of the memory hierarchy, like SSDs and disks. So you can actually choose, I'll keep this data on disk, and you can also choose, so that lets you control a little bit of where it goes. Yeah. No, it would be interesting to do that. So by the way, something I didn't mention, but this model, like, there's nothing stopping you from doing it on a multi-core as well. And in fact, it might be useful because it exposes a bit more detail about the computation. It might actually be useful to do this on a multi-core. So yeah.
How well does the compiled Scala compare to the C++ that Google generates? I mean, what's machine code?
Oh, I see. Yeah, so Scala's machine code, it's not great, although it kind of depends what you do. It's partly like basically Java is actually not bad at generating machine code if you sort of break it all into one function, and you use for loops and while loops and things like that. It's worse when you have polymorphism. So when you say you're iterating over a collection and you view it as just a java.collection, but actually it's an array list, it may not always inline things with the assumption that it's an array list. So there's actually one interesting line of work that some people are doing in the Scala research community is compiling Scala to better native code, or even running it on GPUs, because it's a functional thing. You can learn a lot about what it does. Yeah, but now I'm sure that now we're probably like a factor 3 or 4 off from if you wrote C code. But the interesting thing is, like, even Google's writing a lot of these applications in Java now. It's just for programmability.
So I was curious if you ran into any problems with JVM in terms of either memory management or sort of edge cases, because you're...
Yeah, memory management is a problem on the JVM. The closest thing, like the best thing you can do actually is avoid using the Java heap. So just store data in your own buffers. You'd have to store it as just bytes, so you'd have to turn it back into objects as you iterate over it. But essentially, short-lived objects are not a problem in Java, but long-lived objects are. Because the GC is optimized for short-lived objects, right? Yeah. Yeah. So if people are interested in this from like a PL or numerical side, I'd actually be really curious, to talk to people about how you do other things on it. But hopefully it's given you some idea. So final thing I want to say, just if you want to learn more about it, there are these websites about both Hadoop and Spark, and there are actually video tutorials online for both of them now. So you can really so you can actually play with this if you want. Yeah.
So. Let's thank the speaker.
Okay.
So, and you're in the AMP lab if people want to come and talk to you, right?
Yeah, I am.